Hello, everyone, and welcome back to Know for GCSE. Sorry for the delay on this stream. I got caught up in trying to fix this, but I'm glad you guys are all here. So, today we are going to, what we were going to start doing is English language, but we're actually going to start with English literature today and spend 2 hours in English literature. So, today we are doing poetry revision. So, I'm unsure whether you do the Love and Relationships anthology or whether you do the War and Crime one. Today we're going to be revising the Love and Relationships poems and we're going to be looking at some comparisons. Okay? Okay. So I'm just going to share my screen, and what I'm going to be doing is I'm going to be going through some comparisons for English literature poetry, and yep, we'll be revising those. So let me share my screen. We'll be doing the Love and Relationships anthology, so if you don't do Love and Relationships, feel free to tell me and hopefully I might be able to change it, but let's see. Okay. So let me just type up what we're doing. So love and poetry relationships. Okay. So what I did for my GCSEs was when I had the poetry comparisons essay part of it, I planned out, so a mildly detailed plan for every possible comparison in poetry so that I was prepared for anything. And there were roughly 10 or 11 comparisons that I made. They all came out useful and it all worked in the end so that you will at least you always have a plan for whatever poem that's given to you, because you're given one poem in the question and you're asked to compare it against another poem that you've studied in the anthology. So I'm going to start off by listing out all of the poems in the Love and Relationships anthology for AQA. So there's Walking Away, Mother Any Distance, so it's the first comparison. Then I did Walking Away and Eden Rock. When We Two Parted and Neutral Tones. Actually, I think it will be better to type this out. Sorry, let me just go back over this. So in terms of how I found the poems that I chose to compare, what I did was I used videos and resources online and compiled loads of things together and ended up compiling them into a good resource that we can use now. So let me write down and bullet point them. So we have Walking Away, and Neutral Tones. Just turn my volume down. Walking away and motherly distance. Mother. Okay. Then we have walking away and Eden Rock. When we two parted and neutral tones. Winter swans and neutral tones. Eden Rock and follower. Follower and climbing my grandfather. Sing song and Sonnet 29. Sonnet 29 and Letters from Yorkshire. Love's Philosophy and When We Two Parted. Farmer's Bride and Porphyria's Lover. Before You Were Mine and Farmer's Bride. And those are all of the comparisons that we look at. So in this session, we're going to go through each of these comparisons and find some similarities, some differences, some things you could have. I'm going to give you some tasks. So your first task is going to be that you are going to aim to try and find some similarities and some differences about each of the poem comparisons. So that is going to be your task, and I'm going to give you 30 minutes to find out a point of similarity and a point of difference in each of the poem comparisons. everyone, so we're just doing some comparisons, and I've started off with Farmer's Bride and Porphyria's Lover. So I've started off by saying that they both show possessive relationships through male dominance. However, in Farmer's Bride, he conveys his frustration through animal imagery, whereas in Porphyria's Lover, the frustration is conveyed through pathetic fallacy. Now we're looking at some evidence. So in Farmer's Bride, the title depicts that a woman's importance is defined by her relation to a man, and the fact that the female protagonist remains nameless throughout the entirety of the very long and extended poem suggests that her identity was important both on a social level as well as towards her husband. Now we wanted to relate this back to the theme of how does it show possessive relationships through male dominance, and I said that the quote, caught her, fetched her, turned the key upon her fast. It shows a dominant male oppressing his wife's struggles against her struggles, and also if you focus on the her, it not only suggests that she's like a separate entity, but the lack of love in this consistent and repetitive pronoun suggests that they're so distant, and that's why she's running away. And then we look at Porphyria's Lover. So he says, and last she sat down by my side, and the caesura here conveys his frustration and anger, and his irrational anger. Furthermore, the possessive pronoun my, which we saw in Farmer's Bride as well, foreshadows the possessive relationship. Now, we also see throughout Porphyria's Lover masculine rhyme. Now, masculine rhyme is just a type of rhyme which is prevalent throughout the poem, where the final syllables rhyme. So instead of the consonants rhyming, it's when the final syllables rhyme. And it just suggests how tightly controlled the system is, because this masculine rhyme remains consistent throughout the entirety of the poem. And therefore demonstrates his suppressive control on her, and how he's very tightly controlling her. However, the long and sprawling verse structure just highlights how the speaker is irrational, because the entire poem's structure long sprawling verse which just displays the irrational nature, linking it back to the male dominance and how that is an irrational idea as well. So remember, it's important to integrate comparisons, so don't just speak about Farmer's Bride in a paragraph and then Porphyria's Lover. Try to mix up a little bit. Now, another quote which is important in Porphyria's Lover is when he says, "Spread over all her yellow hair." Now, this suggests how she's consumed him. This idea of all her yellow hair, this idea of being, entrapment, and this idea that the irrational male speaker believes he is the one who is being entrapped, when in fact it is her who's entrapped. And the idea that he views all her yellow hair as dominating him, and he is threatened by all-inclusive love. He's threatened by it, and it shows how the male dominance is actually quite weak in a way. Okay. Now, we also discussed the pathetic fallacy. So in Farmer's Bride, there's animalistic imagery. So we see this animalistic imagery in when he says, like a mouse. Or he says, shy as a leveret. Okay, so when we hear like a mouse, or when we hear shy as a leveret, this tells us that he not only dehumanizes her with this animalistic imagery, but he also, in a way, infantilizes her by comparing her to animals who are unable to think for themselves. And it runs closely to this idea that the farmer, whose occupation is to look after animals and but treat them as animals, treats his wife as an animal, and how men treat women often as animals. And that's what the poet, who's a female by the way, is critiquing about the society. And that is her aim. Now, we talked about the animalistic imagery in Farmer's Bride. We also want to talk about the pathetic fallacy in Porphyria's Lover. So pathetic fallacy is when the weather is used to create a foreboding sense of whatever the mood is. So in this case, we see the weather being used when he says, the rain set in early tonight. The rain set in early tonight. Sullen wind. So through this idea of rain and sullen wind, especially this adjective here, which by personifying the wind, which is another technique, personification here, by personifying the wind, it creates this looming sense of sadness and even grief, which is soon to come. And the idea of rain, this idea of annoyance and petulance, is reinforced here. And one more thing that we can use to compare Farmer's Bride and Porphyria's Lover is that in Farmer's Bride, he is open about the failure of the sexual relationship when he says the stare betwixt us. So in Farmer's Bride, the narrator is open about the failures and how he yearns for that sexual relationship. Whereas in Porphyria's Lover, he tries to convince not only the reader but himself of otherwise. He says, when glided in Porphyria. Now, this has, when glided in, has supernatural connotations. It could have some possibly sarcastic intent behind it, however, a positive thing to also all the warm. As well as give herself to me forever. Which all creates the sense of like warmth from the rain, this idea that there is no issue within the relationship and that it's all okay, and give herself to me forever, as if instead of being a gruesome murder, it was a noble sacrifice. And through this portrayal, it not only creates a sense of very irrational speaker, but also the fact that he's trying to mask his actions as something that is noble, and as opposed to the tragic and gruesome death that she receives. So we've revised Farmer's Bride and For Your Mind and Farmer's Bride and Porphyria's Lover. Let's now move on to Love's Philosophy and When We Two Parted. I hope to not be too long on this, but it was a good start. So okay, now moving on to Love's Philosophy and When We Two Parted. Okay, so the first thing I want to say is that both poems explore the desperation in romantic love through nature. So the first point we could say is both explore desperation in romantic love through nature. So in this topic sentence, it's really good because we've got this idea of the theme, so desperation, the mood, as well as the method used behind it. So both explore desperation. So let's see, how is this achieved? So the first way this is achieved is in Love's Philosophy. We sense this idea of the dew of the morning, the dew. So there's a constant repetition of the dew of the morning. And the dew. So this is the last remaining evidence. This love no exists. Unlike in Love's Philosophy, When We Two Parted, it uses fewer literary devices to perhaps convey the incomparable nature of intimate relationships, or alternatively, that intimate relationships should be kept private. So, oh, I'm so sorry, this is the wrong quote. That's why it did not fit quite well. So we get this idea that both poets use semantic fields and these semantic fields are used differently to express their portrayals of love. So both use semantic fields to convey their portrayal of love. So what we mean here is that in When We Two Parted, in Silence and Tears, Byron uses and focuses on human nature, whereas Shelley explores the supernatural nature of love. So When We Two Parted was in Love's Philosophy. Shelley explores the supernatural of love. Therefore, what is being said is that both poems explore desperation in romantic love through nature. However, the semantic fields are used differently to convey their portrayal of love. So in When We Two Parted, there's a focus on human nature, whereas in Love's Philosophy, there's a focus on supernatural. On the supernatural. So we see in When We Two Parted, there's this constant repetition of the dew of the morning, as well as the dew. And both of these quotes highlight how it's the last remaining evidence of the relationship, as this love no longer exists. So we see in When We Two Parted, there's this focus on nature and the idea of the dew of the morning, and the dew is the fragmented pieces remaining of the relationship. Now, by contrast, in When We Two Parted, in Love's Philosophy, in When We Two Parted, fewer. So we see here that there's very few language devices used in When We Two Parted. But in Love's Philosophy, it's much more fantastical. So we see there's a juxtaposition in Act 1, in stanza 1 to stanza 2. In Love's Philosophy, we see fountains, from fountains to moonbeams. So this more fantastical depiction of love in Love's Philosophy has much grander supernatural imagery instead of earth-like imagery through this personification. And this emphasizes his increased desperation. That it is not only it's not only worldly want, but it is a universal and fantastical. So therefore, this acts as another method of Shelley's rhetoric, which is the art of persuasion. So another method of his rhetoric in order to convince that he wants to be loved. But there's also this idea alongside this, the fact that the use of moonbeams suggests that just like his quest for love, and the moonbeams, they are both unattainable and unevidenced. Now, we don't only see this shift from stanza 1 to stanza 2 here, we also see this shift when we go from mix to clasp. Now, this transition of physical verbs highlights the forced love that he so yearns for. It's been 45 minutes now and we've only got through the third one. Okay, that's fine. We'll have to hurry up. Now, both poems emphasize on the unattainable. So in both poems, emphasis is placed on the unattainable. Considering Shelley and Byron's backgrounds, perhaps is a reference to the illicit and intimate affairs that must be kept quiet. So there's this idea of the semantic field of nature to supernatural, how in Love's Philosophy there's more fantastical imagery, whereas in When We Two Parted it's generally quite straightforward and boring. Now we have our second line of argument, or second topic sentence, which is that both poets' alternate use of structure either acknowledges the boundaries or challenges them. So both of the poets' inclusion of structure either merely acknowledges the challenges they face, or challenges them. So we definitely see that the challenges them is part of the Love's Philosophy, and the acknowledging of the challenges is part of When We Two Parted. However, how do we evidence this? So let's look at Love's Philosophy. What is the structure of Love's Philosophy in comparison to When We Two Parted? So the structure of Love's Philosophy follows like a philosophical argument. Which is perhaps predicted or foreshadowed within the title itself. And the title itself becomes its own oxymoron when we realise that Shelley's attempt to prove logic within the complex emotions of love merely show his devout desperation as opposed to a successful argument. So Love's Philosophy has a philosophical argument, as if it's constructed, and it even ends with a rhetorical question. Ironically, Shelley aims to prove logic within the complexity emotions of love in order to persuade love. However, he only seems to distance himself from the prospect of love through this rather unromantic sense of desperation. The rhetorical question he ends with is, why not I with thine? Now, this contrast highlights the injustice and lack of logic in his demise. And also this idea that he has switched the usual order of the sentence. It would normally be structured something like why are you not with me, but the position of I suggests that his focus on, despite being a love poem, is on his own selfish interests. Therefore, I would doubt whether he's very successful in romanticizing it. Furthermore, there's a lot of repetition used in Love's Philosophy. And the repetition is used to assert his unchanging views. We see anaphora of and the. Now, this suggests that he's unchanging and he is, obtuse and unwilling to mold his views upon anything. I feel like within this poem we learn more reasons why he is not an eligible bachelor. Now we also see a semantic field of embrace. Within love's philosophy, such as mingle, mix, clasp, and kiss. Now, not only is there a semantic field of embrace, but it also has this audio effect of very soft and smooth in the through these slight sibilants of mix and clasp and kiss, and it's trying to gently encourage his romantic endeavours. Now, consistency in form as well demonstrates his unchanging desires. Unchanging desires is not only delivered through the repetition, but it's also delivered through the consistency in his form of the poem. We see the rhyme structure A, B, A, B, C, B, C, D, trochaic meter, as well as ballad meter, and it's just continuous. Now, ironically, this rhyme scheme is exactly the same as When We Two Parted. A, B, A, B, C, D, C, D. So they share the same rhyme scheme, which is another lovely reason to compare them together. Now let's look at When We Two Parted and how When We Two Parted's inclusion of structure either merely acknowledges the challenges or challenges them. So in When We Two Parted, we definitely see the writer clearly just acknowledge. We see this cyclical structure, which again capitalizes on this idea, on this suggestion that the relationship is irretrievable. Furthermore, the beginning and end shares both silence and tears. And this highlights the hopeless and unending connotations of death as well in this silence and tears, as if mourning for the relationship was death-like, which is ironic because the writer himself was quite the womanizer. And also, repetition is used in When We Two Parted, but not in the same way as love's philosophy. So, in repetition was used to declare his unchanging views in love's philosophy. Here, repetition is used to demonstrate the regularity of the writer's sadness and how it's seemingly endless. Okay, so that's another poem compared. Love's philosophy, When We Two Parted. So we've now done 3 poems comparison. It's now time to move on to another one. So let's compare Sing Song and Sonnet 29. So in terms of Sing Song and Sonnet 29, both poems explore fantastical depictions of love. So both poems implore and inquire after fantastical depictions of love. Now, in Sonnet 29, Sonnet 29, the conceit is being employed through the extended metaphor that implies that sexual and spiritual aspects of love, which show how all-encompassing love can be. So it's quite a long thing to say. So the conceit just means the main idea. So the conceit in Sonnet 29 is employed through the extended metaphor metaphors which imply how all-encompassing love can be through the heavy assertions of both the sexuality and the spirituality of love. So when we look in this case, the whole poem is regarding the bands of greenery that swamp and engulf the tree. So here we have this idea that she says, "My thoughts do twine and bud thee like wild vines above a tree." So we see the sexuality in her intent through the words wild, and also bud was contemporarily words used for female genitalia. And then the spiritual nature of the bands of greenery comes from the word thee. And there's just a overall continuous use of quite archaic language. And through the archaic language, we get the sense that the love is both modern in terms of its openness and sexuality, but also remains traditional to God. There's lots of sensory imagery as well through burst shattered everywhere. In Sing Song, the conceit is the idea that value is balanced between the shop's produce as well as value for his own wife. The plethora of monetary language, such as half price, charge, these all have connotations of money, and it highlights her importance to him above all material wealth and responsibility. Okay, so we've now sort of completed the love and poetry relationships revision. We've done 1, 2, 3, 4, and we moved on to 5. So we've gone through half of it. I now am going to move on to revising some maths. So let me get the presentation up. We're now going to go to revising maths. And we'll complete all of that. Since yesterday we did start off from the maths, and now we're just going to, so let me just get the resources. Okay, everyone. So it's now 10:01 and we're going to be doing some maths revision. So let me just change the title of this. And we're going to start from velocity time graphs, because this is a lot of people struggle with. So we know quite well about distance time graphs, but velocity time graphs are a thing that definitely people have issues with. So a velocity time graph, on the y-axis we have the velocity, and on the x-axis we have the time. Time graphs tend to have curves like this, and what they will normally want you to do is find the distance travelled. Now, the distance travelled with the velocity time graph is actually the area underneath. Oh, is my sound cutting? I believe it's cutting a little bit. Do tell me. Okay. I'm going to try and carry on anyway, because I think you'll still be able to see on the whiteboard anyway. So here is the velocity time graph, and the distance is the area under the graph. And in order to find the distance when there's a curve, what you have to do is you have to split it up into sections. So using your pen, split each section up like this, and you'll realize that each part is like a trapezium in this case. So you do from here to here to here to here to here. So what you would do is you would just find the area of the trapezium and the area of the multiple trapeziums, and then just add them all together, and then you would eventually get through. And in order to find the total distance, what you do is we know that the area of the trapezium is the height divided by 2 multiplied by a plus b, where a is one side and b is the other, and this would be the height here. So in this case, we've got this but turned around, so the trapezium is turned like this, or perhaps the other way. And there's loads of questions on this. If we flip this, there's loads of questions on this in GCSE maths. So in order to do this, what you would do is you would do the height. So the height is actually the class width. So this is the height. So you would do the height divided by 2, the class width divided by 2, multiplied by, and then you would do the a plus b. So the a plus the b, and then the a plus the b, a plus the b. But what you'll notice is that each of the numbers from here to here will be repeated twice, and then the first coordinate and the second coordinate will only be used once. So what you do is you just put the first value and then the last value, so say if that's 5, and then you do 2 times all the values in between. Okay, there's a bit of internet issues, unfortunately, which is why this is cutting out. Do tell me if you can still hear me or not. I'm so sorry. Okay, so we're just going to resume back to where we are. Okay, so the height over 2 multiplied by the first coordinate, multiplied by the last coordinate, multiplied by 2 times every coordinate in between, and that will be the distance. Now, it's also important to note that in a velocity time graph, the gradient is equal. Now, we covered this in our physics this morning, and it's quite important to remember that. Therefore, if we know that the gradient is acceleration, then we know that acceleration is equal to the y value, which is velocity, divided by the x value, which is time. So acceleration is the change in velocity over time. That's what we looked at in physics this morning. Now we have equations of motion, which is Suvat equations, basically. So let's look at equations of motion. Now, if an object is travelling at a constant speed, then speed is equal to distance divided by time. However, if you're travelling at constant acceleration, then we have a different equation that we use. So, speed is equal to distance over time is for constant speed. Remember, we have the graph distance, the gradient is speed. So when we have constant acceleration, then we have some more things. We have a graph which has velocity, a graph that has time, it has a curve we know the gradient is acceleration, and that the area underneath is equal to the distance. Therefore, the equation to find the constant acceleration will have a lot more things in it. So it will have, and that's what we call them, the Suvat equations. So in terms of the Suvat, S is displacement, which is just the vector quantity for distance, which just means like the exact distance. So distance would be, say, if you wanted to go from A to B, but you went this way, that's distance. But displacement is A straight to B, the angle travelled. So that's why it's a vector quantity. But anyway, let's look at the Suvat equations in more detail. So Suvat, each letter is representative of a different metric. So S is for displacement. If it's easy for you to remember, just remember S as distance. U is for initial velocity. And V is for final velocity or current velocity. And then A is for acceleration. And T is for time. Now we have different equation proofs. You may be asked about equation proofs, but what you'll more likely be asked is just to use the different equations. So the different equations, you have v squared is equal to u squared plus 2as. You then have v is equal to u plus 2at. You have s is equal to u plus at squared. And then you have s is equal to half u plus v times t. So we have these four different equations. The purpose of having four different equations is because if you have one of these values that you want to find, you can then use any one that you please. You're going to have to memorize these in your exams as you're going to be given them. I'm not sure if the 2023 exams are going to be given them or not, so you will have to check. And let's do a question. So, a train is travelling with an initial speed of 4 meters per second. So we're told the speed is 4 meters per second. It increases its speed to 7 meters per second. In 10 seconds. At a constant rate. So what distance did they travel in this time? So for this question, we're going to be asked what the distance is. So in order to answer this question, we're just going to use one of the equations. So we know that s is the distance, s is half u plus v multiplied by t. Now we know that the distance is what we're finding out. U plus v is 4 plus 7. And then you're timesing it by t, which is 10 seconds. So your final answer should be 55 meters. Now there's a part. The part B is find the acceleration. So in order to find the acceleration, we can use another equation. So let's look at so we know that the initial velocity or initial speed is 4. The final velocity is, the time is 10, and the distance is 55. So we have a choice of which one we can use now, but I'm going to just use the v is equal to u plus at. So we then get 7 is equal to 4 plus a, which is what we're trying to find out, multiplied by 10. And overall, you just get a is equal to 0.3 meters per second squared. Okay, so we're now going to look at graphs of a circle. There's a lot of internet issues going on here. Okay. Now, let's look at one example. Find where the line x minus y. The first question is, find where the line x minus y. Oh my goodness. Find where the line x minus y is equal to 1 meets with the equation x squared plus y squared is equal to 13. So what you do here is you just rearrange this equation, as we know that x is now y plus 1. So what you do here is you just replace it, so you do 1 plus y squared plus y squared is equal to 13. Now 1 plus y squared, this gives us y squared plus 2y plus 1 plus y squared is equal to 13. So then you get 2y squared plus 2y minus 12 is equal to 0. You can now divide this by 2 and you get y plus y minus 6 is equal to 0. And then you now have a quadratic and you get y plus 3, y minus 2. So then we know that y is equal to negative 3 or y is equal to 2. And then when x will then equal minus 2 or 3. And that's our answer. Now we've got another question. So let's do this other question. Find where an equation of the tangent to the circle x squared is equal to 25 at the point 3, 4. Find an equation to the tangent of the circle x squared plus y squared is 25. So what we can do here is we know that the tangent is perpendicular. So we know that this circle, first of all, has its center in the middle. And we know that one point is 3, 4. This is exactly where the tangent lies. So we know that the tangent is perpendicular to the radius. And therefore the tangent will have a perpendicular gradient to the gradient of the radius. So the gradient of the radius, firstly, is the change in y values, which is 4, over the change in x values, which is 3. Now we know that the tangent is perpendicular to the radius, so the tangent's gradient will be minus 3/4. Now we know that the equation of any straight line is equal to y is equal to mx plus c. And we know that the gradient is already minus 3/4 x plus c. And we can now plug in this coordinate 3 and 4. So plugging in 3 and 4, we get 4 is equal to 4 times 3 plus c. So 4 is equal to minus 9 over 4 plus c. And therefore, c is 25 over 4. And we have the equation. So y is equal to minus 3/4 x plus 25 over 4. Okay. And in terms of other complex graphs, like graphs of a circle, reciprocal graphs are also quite important. So reciprocal graphs will have the equation y is equal to k over x, in which k is any value. And x and y are asymptotes to the curve. So if we look at what a reciprocal graph would look like, a reciprocal graph would look like this. They're asymptotes to the origin. Okay. So now we've looked at reciprocal graphs. It's also important to note what do cubic graphs look like. Because we know quadratic graphs look like either this or this. So cubic graphs actually look like this. But it could also look the other way if it was negative. So if it was negative, it will look like that instead. So reciprocal graphs look like that. These are for cubic graphs, and these are for quadratic. Okay, now we know and are familiar with the different graphs. Let's just do a bit of a revision on the different types of areas and the different volumes of shapes. So, area of a trapezium, as we've been through, is the height over 2 multiplied by a plus b. Now, the definition of a prism is any shape, a 3D shape, which has the same cross section all the way through. All the way through. Now, area of a circle, hopefully you should know this by lots of practice. Area of a circle is pi r squared, and circumference of a circle is 2 pi r, or if you want, pi times diameter. Now, area of a sector is going to be x over 360, where x is the angle of the sector, multiplied by pi r squared. And then if you wanted to do the arc length, would just be x over 360 times the circumference, which is 2 pi r. Now, if you wanted to look the volume of a cylinder is going to be the area of this surface multiplied by the height. So that's quite easy to do. The surface area of a cylinder would be 2 pi r squared, because what we're doing is we're timesing the area twice, and then to find the area of this part, we then do 2 pi r height. And the reason we do that is that you can imagine it as if we've got 2 pi r, which is the circumference, a really long extended circumference. Finally, let's just look at volumes of prisms and cones. The volume of a pyramid is 1/3 times base area times height. That's what the volume of a pyramid is. And the volume of a cone is 1/3 times height. Because remember, the base area of a cone is the area of a circle. Now the curved surface area of a cone, which when we're talking about that, the curved surface area is this bit here. So the curved surface area of a cone is pi times r times L. L is a slant height. And then the base of the cone would just be pi r squared. And finally, the last one, the volume of a sphere is 4/3 times pi r cubed. 4/3 pi r cubed. Okay. So now we have done area and volume. We are now going to be moving on to another topic of maths that people tend to find, which is equality and inequalities. So equalities are not actually called equalities, they're called equations. And inequalities are just the opposite. So when we have sort of things we can look at. So what I mean by this is, let's start with quadratics. So sometimes you'll be asked to find the roots of a quadratics, which is basically what you get when you solve a quadratic. However, sometimes they can be super difficult. So say if we had x squared minus 2x, and they'll say find the roots of the quadratic. So what you'll do is you'll times to get 0, and you'll add to get minus 2. So what adds to get minus 2 and times is to get 0? Minus 2 and 0, right? So minus 2 and 0, and then you get x is equal to 2. So you find the roots, x is equal to 2 or x is equal to 0. So let's do this equation. First of all, can we remember what the quadratic equation is? Let's try and remember. So the quadratic equation is x is equal to minus b plus or minus root b squared minus 4ac over 2a. Let's do that again. X is equal to minus b plus or minus root b squared plus 4ac over 2a. x is equal to minus b plus or minus root b squared plus 4ac over 2a. That is a quadratic formula. And you're going to need to know that off by heart unless it's taken off the exam, but I don't think it is. So you're going to need to know that off by heart. Okay. So let's put it into action. So say if we wanted to find the red, 5x minus 2, what you would do is you know that 6 is equal to a, b is equal to minus 5, and c is equal to minus 2. So when we have the quadratic formula, which is minus b plus or minus root b squared plus 4ac over 2a, then what you would do is we're putting them into the equation. So we've got minus b, but we've got minus 5, so that would just be 5 plus or minus root b squared, which is 25, plus 4 times 6, which is 24, times minus 2, which is minus 48, over 2 times 6, which is 12. And your total answer should be 1.13. Now we want a completed square. And writing stuff in completed square form. This is another aspect of maths that people tend to find a bit scary. So, completed square form. This is just when you write something like this: x plus a squared minus b. Okay? X plus a squared minus b. So let's do a practice question of how to do it. So express x squared plus 4x minus 3 in completed square form. To do this, we're going to start off by writing x, and then you do 4 over 2, so x plus 2, and then square this, and minus the square of this. The square of this is 4, so minus 4, and then do whatever this is doing here, so minus 3. So your answer should be x plus 2 squared minus 7. Okay, now it's a bit different when we have a coefficient of x. So let's do a problem where we have the coefficient of x. So we have a coefficient of x. We've got 2x squared plus 4x plus 1. Now what we do here is we take the 2 out. We do x squared plus 2x plus half and leave it as fraction. Don't put this in a decimal form because it's much easier in the long run. So now what you would do is you would just complete the square as normal. So x plus 1 squared minus 1 plus half multiplied by 2. And then you get x plus 1, 2x plus 1 squared. So minus 1 plus half is minus 3 over 2. Oh, no. It's minus half. So 2 times minus half is minus 1. And that should be your answer. You can also solve quadratics by completing the square. Completing the square is super nice and useful. Now, with completed square form, you can also find things such as the minimum point or the maximum point. So whatever you get in your completed square form, so you get y, for your completed square form, you get y is equal to x plus a squared minus b. Whatever you get for your a and b values, it turns out that minus a, b is equal to the minimum point of your quadratic. And when we say minimum point, we mean this point here. We're at the bottom part of it. So the turning point. Okay. Now we are going to go on to simultaneous equations, which are relatively simple. But I think we'll focus on regions and inequalities now. So let's look at quadratic inequalities. Quadratic inequalities are things like this. You've got x squared minus 7x plus 12 is less than or equal to 0. So this is the inequality. And now what they would ask you to do is solve the quadratic inequality. Now what you need to do in order to solve this quadratic inequality is begin by factorizing the quadratic as normal. So what numbers multiply to get 12 and add to get 7? Well, that's x minus 3 and x minus 4. So you factorize as normal, and then you sketch a graph. So we know that the turning points are 3 and 4. So the graph would look something like this. And now what you do is we read what this one says. We're saying that this, which is also equal to the y value, they're saying that the y value must be less than or equal to 0. Now, if the y value is less than or equal to 0, we're talking about it can't be above here. So it's going to be between these two values. Therefore, our answer is going to be between the values of 3 and 4. Okay. Now let's look at another type of quadratic inequality. Here, the quadratic inequality looks like this. So solve x squared minus 3x minus 10, and how that is greater than or equal to 0. Now, as we do normally, we factorize first. So find two numbers that multiply to get minus 10 and add to get minus 3. Those two numbers are minus 5 and plus 2. So x minus 5 and x plus 2 is greater than or equal to 0. And now what we do is we draw a graph and write down the turning points. So we've got minus 2 and 5. And we draw it. And now we're told that the y value is greater than 0. So if the y value is greater than 0, it's going to be from here and here, because it can't be anything below this line here. So that means that the y value has to be less, the x value has to be less than or equal to minus 2, or greater than or equal to 5. And that's the answers that you should get. Now we're going to do some probability. So when there are m ways of doing x and n ways of doing y, the total number of ways of doing x and y is m times n. So we'll talk about that later. So let's look at Venn diagrams. Okay. So let's label this Venn A and this one B. and this is the universal set. Okay. In maths. So firstly we have PA at NB. Then we have PA or B. And then we have P of A. And then we have P of B. And then we have mutually exclusive. So what do these symbols mean? So P, when we have P brackets, whatever, it's just saying the probability of this thing happening. So in this case, the first one is a probability of A and B happening. So if it's a probability of A and B happening, it must be limited to this center. Okay, so that's the probability of A and B. Now, if you wanted to do the probability of A or B, then it will be all of this covered. Because it's the probability of getting A or the probability of getting B. So it includes the center. Now, the probability of getting just A will be any of these values here. The probability of getting A. Because it doesn't say the probability of getting A and not B. If it was a probability of getting A and not B, it would look okay. And the probability of getting B looks like this. Now, mutually exclusive is a term that we're going to come up with. So two events are mutually exclusive. One outcome excludes the possibility of another outcome happening. So you're therefore shrinking the sample space. Okay. So this is an example of this is, say you can only study French or geography. And if you study French, you can't study geography. So therefore, if you're saying all the people who study geography don't study French, then you're limiting the sample space to people who don't study French, as opposed to all the students in the year. So it's just when you're limiting the sample space. Okay? So in terms of mutually exclusive, the Venn diagram would not even look connected, because there can't possibly be an intersection if one event excludes the outcome of another happening. So that's what a mutually exclusive Venn diagram would look like. Now, continuing on from probability, let's look at and a bit more. So the symbol N. So provided two events are independent, meaning that one event occurring does not affect another event happening, so it's not mutually exclusive, then you can just times the probability of A and B occurring. So in this case, for example, we said the probability of A and the probability of B is this section here. So in order to work that out, you can just do the probability of A multiplied by the probability of B to get the probability of A and the probability of B. They are equivalent both sides. Okay. For example, the probability that it's sunny tomorrow is 1/5. Now the probability that you're going to win the lottery is 1/20. So the probability that it's sunny and you win the lottery would be 1/5 multiplied by 1/20, which is 1/100. Now, or. So and is when both things can happen at the same time. Or is when we're talking about something that's mutually exclusive. So let's talk about or. Mutually exclusive. Now, what that then means is that they cannot occur because one of the events stops the other one from occurring. So, for example, the probability that it's raining outside excludes the probability that it's not raining, right? So both of these probabilities can't exist at the same time. It can't have raining and not raining at the same time. So that's an example of mutually exclusive. So let's look at an example. The probability that it's raining is 0.1, and the probability that it's not raining is 0.9. So if you're asked to find the total probability of whether it was raining or raining, what you would do is you would add. And when it's an and, you would multiply. So you've got to remember that in your head. And you multiply the probabilities, or you add the probabilities. Okay. So that's enough of probability. We are now going to move on to a bit of conditional probability. Actually, we're not done completely with probability. Okay, let's get on to conditional. So conditional probability looks like this. So conditional probability is when you're given extra information that shrinks the sample space. So it's represented by the symbol of the almost slash, the line. So this symbol here represents conditional probability. I'm going to just call it conditional. So let's look at an example of this. So the probability that you have A knowing that it's out of B, knowing that it's B, is the probability of having A and B divided by the probability that it's just B. So aka, this is when the probabilities are dependent on each other. So this is saying the probability that we have A, provided that it's in B, is the same probability as having A and B in the probability of B. So let's just look at an example, because this can get confusing quite quickly. So this Venn diagram here will represent the students' A-level choices. We've got French and we've got German. And this is the universal set. And we've got 46 people who don't do German or French. You're going to now be asked questions about this Venn diagram. So you want to find the probability. Question A. Find the probability that a randomly selected student studies German. Now remember, in order to do this, all we have to do is say that because it's randomly selected, that can be out of any of the students, and we know that the total amount of students is 46 plus 7 plus 3 plus 8, which gives us 64. So out of 64 students, 8 plus 3 study German. So 11 out of 64 people study German. That was relatively easy. B. Find the probability that someone studies French and German. Now remember, French and German, that means that we're looking at this section here. So again, it's someone, so it can be anyone. So it's again out of 64, but it's only 3 out of 64. Now we're going to get a bit hard. Find the probability that they study French given that they've studied German. So that is the conditional probability part now. So what you would do here is, we know that the probability that they've studied French, so let's do some working here. The probability that they've studied French is 7 plus 3, so 10 out of 64. And we're told this, but we're told that given that they study German. And we know out of this 10 out of 64, 3 of them study German, so therefore we have 3 out of 64. Now the final question to this part D. Find the probability that they study German given that they don't study French. So we know that out of everyone, the people who study German are 11 out of 64 of the people. But we're told that they don't study German. And 3 of these 11 people do study, they don't study French. 3 of these 11 people do study French, so it will just be 8 out of 64, which is the same as saying 1 over 8. Feel free to simplify the probabilities. Okay, I hope that makes sense. We are now going to look a bit at congruency, and then trigonometry, circle theorems, and functions. Okay. So let's look at congruency. If this is helpful, do let me know, because I want to be as helpful to you as possible. So congruency. ABCD, we're going to look at an example. ABCD is a parallelogram. Now, triangle ABC sorry, not ABC. Triangle, ABC is congruent. Now, the definition of congruent is exactly the same in all sizes and all angles, okay? So triangle ABC is congruent to triangle ADC, and we have to prove this congruency. So how do we prove this congruency? There's different ways to prove congruency. So we've got angle, 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 side, side, angle, side, angle, right angle, hypotenuse side, and side, side, side. But first, let's use the information that's given to us. So we know that it's a parallelogram. So knowing that it's a parallelogram, we know that length AB, let me do it in this, length AB is equal to length DC. So that is side. Then we know that length AC is common to both angles. We can see that clearly. Let me do it in this. AC is common to both triangles, so that therefore is another side. And finally, we know that length AD is equal to length BC. So this length is equal to this length. So that is another side. Now, unfortunately, they won't be giving you the questions in GCSE maths. It might be harder. But if you do see a question like this, always make sure to end your proof by saying by and whatever proof you use. In this case, we used side, side, side. Okay, let's do a more tricky one now. So we've got 2 lines here and 2 lines here. And we've got A, B, C, D, and E. So given that AB equals DE, prove that triangle ABC is congruent to triangle CDE. Okay, so we now have to prove congruency between this triangle and this triangle. So let's begin. So we know that AB is equal to D because we know that we're told by these two are parallel lines. So therefore, AB must equal DE. So that's side. Now angle CAB. So CAB, which is, let me mark it with this, which is this angle here. Angle CAB is equal to angle CED. And this is because of alternate angles. So that is angle. And finally, we can do the same thing with angle ABC and angle CDE. And say angle. So we have angle, side, angle. And that is a rightful proof. So we can say hence congruent by angle, side, angle. Okay. Now let's move on to some. If you have any questions on the topics, feel free to put them in the chat and I can pause and go through them. Okay. So now we're going to look at things like sine graph and cos graph. So it's important for you to know the values of sine graph and the values of cos graph and what they look like. So you can imagine them as opposites to one another. So sine graph at 0 is also at 0. And then at 90 degrees is 1. And then at 180 degrees is back at 0. 270, it's at -1, and so on. So we get this shape of graph. That is what the sine graph looks like. The cos graph is opposite. At 0, it's already at 1. At 90, it's at 0. At 180, it's at -1. And at 270, it's at 0. So it looks like this. So imagine that's -90 degrees. So these are the two graphs, the sine graph and the cos graph. Now, the tangent is a bit of a different graph. So the tangent looks like this. So whenever it gets up to 90 degrees, it becomes an asymptote to x is equal to 90. So it looks like this. So it's 180. So after every 90 degrees, it just never touches that line. And that's the tangent graph. So in terms of tangent, from the graph, you don't have to memorize any values. Just remember that up until 90 degrees every time, it becomes an asymptote curve. Now, the sine graph values. So from this, you know that sine 0 is 0. Sine 90 is 1. Sine 180 is 0, etc. And then from this graph, you know that cos 0 is 1. Cos -90 or cos 90 is both 0. And cos 180 is equal to -. Okay, there are the graphs. And you could get a question like this. In the interval, interval between 0 x and 360 degrees. Find the values of x for which sine x is equal to 0.9397. Give your answer to the nearest degree. So in this question, we're told that we have to find out what x is. So what x value outputs 0.9397? So if we just go back to our graph, we know that with the sine graph, the closest value to getting that is sine 90. So it's going to be around 90. But how do you figure it out without using graphs? So you can just use a calculator and do sine inverse of 0.9397 is 70. But we know that it will never just, because the sine graph looks like this. So it will just keep going. So at some points, it'll hit the hit that point 0.93 multiple times. Therefore, in order to find the other multiple time for sine, the rule is that you always do 180 minus the first value. So 180 minus 70 is 110. And it's within the range specified. So your answers would be x is equal to 70 and x is equal to 110. Now, there's also another rule which you might want to know in terms of relating to trigonometry, and it's the being able to find any area of a triangle with the sine rule that half times AB times sine C. So half AB sine C, in which AB are two sides and C is the angle in between. So that is what you can use. So half AB sine C can give you the area of a triangle. We have some other rules as well. So we have, when you're looking for an angle, you can use the sine rule. Sine A over A is equal to sine B over B is equal to sine C over C. So the capital letters are the angles and the lowercase letters are the sides. Now, that's the sine rule. It's nice and easy to remember. The cosine rule. Oh, and when you're that's the angle. If you wanted to find a side, it will be much easier to do this. But you can easily figure that out. In terms of the cosine rule, for angles, cos A is equal to a squared plus b squared minus a squared over 2bc. So cos A is b squared plus c squared minus a squared over 2bc. That is cos rule. And this is used for when to find an angle A. Now, if you wanted to find a length, you would use a squared is equal to b squared plus c squared minus 2bc cos A. So this form has just been arranged. Just arrange it, but it is a bit difficult. So maybe learning it would be beneficial for you. Okay, we're going to look at transforming trigonometric graphs very soon. We're just going to quickly go over some things before we return to trigonometry. So, in terms of just some revision over box plots and lower quartile, upper quartile, things like that. So this is what a box plot would generally look like, and you will have the scale of what each value means at the bottom. So this is the interquartile range. This is the median. Get confused here. This is the lower quartile. and this is the upper quartile. This is the minimum value, and this is the maximum value. Now, in order to find things like the upper quartile, to find the lower quartile, you would just do n over 4. So n being how many values there are, plus 1 over 4, and then you can that many values in. And so it's that value. The upper quartile is then 3n plus 1 over 4 is that value. Now, when we have a cumulative frequency diagram, so a graph, a lot of people go wrong here, and I have seen this come up in the GCSE many, many times. The cumulative frequency graph looks like this. So you're going to have the frequency on the left-hand side, the time example, so whatever variable on this side, and it will look like this. So what you have here is a smooth curve. So always draw a smooth curve when you're drawing a cumulative frequency graph. And if the table of values would look like this, say, and then, and you've got like 5 and 8, always use the end of this value. So always find 2 on this value, and then you would do 5. You wouldn't find you wouldn't find between 0 and 2, because that would be a frequency diagram. Because we're doing cumulative, it's adding it up to, and then for this one it'll be the end of 4. It won't be the middle. Okay. Now, in order to find certain things, so if you wanted to find the median of a cumulative frequency graph, what you would do is you would draw a line halfway of the cumulative frequency. So in this case, if this table was showing the times taken by 50 people to solve a maths puzzle, so you would just do 50 divided by 2. So you would do the total amount of people divided by 2, which is 25. And then what you do is you find 25 on here, you go up, and you get the frequency at that point. And whatever that is, you will then get the median value. Or it would normally be like this. Yeah. Okay. Let's look at functions. So functions can often be quite confusing, but don't let it confuse you too much. What we'll do is we'll go through some different practices to see what you would do. So the first one would be, for example, let's do this. F of x is equal to 3x minus 2, let's say. Find f inverse x. That's not very clear. F inverse x. Now, in order to find f inverse x here, what you have to do is you have to act as if, so what you have here, f of x is y is equal to 3x minus 1. So 3x minus 2. Now act as if you have swapped the x and y values. So for example, imagine this is 3y minus 2. And then what you want to do is put y as the subject. So make y the subject of the formula. So you would do x plus 2 is equal to 3y. So therefore, y is equal to x plus 2 over 3. And then that would be your answer. So whenever you get an inverse one, what you want to do is you want to flip the values. So swap the x's and y's and then make it subject of the y. Okay. However, sometimes instead of having just x, you have a f of x is equal to, let's say, 310 over 5 minus x. Okay? And you'll be saying, the question will be find f minus 1, 6. So now we have a value here. So instead of, if this was just without the inverse sign, what you would do is you would just replace the x here with a 6. But because there is an inverse sign, you would just put 6 on this side and work it out from there. And you would eventually just get, let's see, x is minus 15. That's what you would get. Okay. We are just going to do a bit of two random topics that I think always forget to teach their students because they think they won't come up, but it has come up before, but it's been disguised as a question. So it would be find the solution of x cubed plus x is equal to 7 to 2 decimal places. Use trial and improvement. So many schools aren't actually taught about trial and improvement. So what you would do here, or it's a very forgetful topic nonetheless. So what you would do here is you would create a table, and in this table you would put your guessed x value. In this side you will put your answer, so what is outputted once you input this guessed x value, and then here you'll put your comment. So let's guess that x is 1, for example. When we put 1, then we get the answer 2. But we know that it's supposed to be 7, so we know that this is too small. So let's move on to a bigger number, 2. When we plug 2 in, however, we get 10. This is therefore too big. Now we know that the number must be between 1 and 2. So let's say it's 1.75. 7.109. This is just too big. So let's do 1.7. 1.7 gives you 613, which is too small. So it must be closer to the 1.75. But remember, we have to give the answer to 2 decimal places. So what we will do here is the vital next step, or let's guess 1.73. Guess one more time, 1.73, and we get 6.907, which again is, so if we guess 1.74, we get 7.008. So this is just, so now we know that the number is in between 1.73 and 1.74. Now don't stop, even though you see that it's already to 2 decimal places. You just have to try it one more time to see if it's closer to the 1.73 or is it closer to the 1.74. So you try 1.735, and when you plug that in, you get a number that's just too small. It's 6.964 or something like that, and that's just too small. Therefore, we're going to go for 1.74 to 2 decimal places. Okay, so that's called the trial and improvement. Now, there's also another method that you may be asked called the interval bisection method. So the interval bisection method, so similar question, solve x squared plus 4x minus 325 is 0. Solve this to 1 decimal place. So for interval bisection, set out your working like this, I would suggest. So say let f of x equal x squared plus 4x minus 325. So now let's plug a random guess in. Let's say 15. So when we plug 15 in, we get 155. Now, this is way too big because it needs to be 0. So let's... Oh no, not 155, sorry. We get 400. Minus 400. Now, this is too small. So therefore, let's go for something bigger. Let's say f is 20. But when we get f is 20, then we get 155. And now we know that this is just too big. So this number has to be between 15 and 20. So the interval bisection, you have to say, so x is between 15 and 20. That is the key part of interval bisection because that is bisecting. So now you can give another guess that's roughly in the middle. So say f of x is 17. You get the answer 32. This is just too big. So we now know, and we have to update this, that the answer is between 15 and 17. And we keep repeating this until we get the answer to one decimal place. Now, the final method of this type of thing is called iteration. So iteration is another calculator method, so you only be asked about it in the paper. And again, it's to do with quadratics. So say you've got the quadratic y is equal to 5. And you're asked to do this to 5 decimal places. So the first thing you want to do is you want to rearrange to make x the subject. So let's make x the subject here. We know that 0 is equal to x squared plus x minus 5. X squared is equal to x minus 5. And then x to the power of 1 is 5 minus x to the power of 0. So that's what you would get. You would rearrange it to get that. And now you find the pattern. So the pattern is x to the power of n plus 1 is therefore equal to 5 minus x to the power of 1. Because that's the pattern here. And then what you do is you apply this to a calculator. So you keep changing the value, and then you keep pressing the equals key on your calculator until the value changes, and then until it keeps repeating. Then you stop, and that's your answer. So you press the value in, for example 13, then you press the equals, and then you keep using the answer key beyond that point. Okay, we're finally going to move on to some circle theorems. Now, in total, there are 8 circle theorems, and you will need to know the proof of these circle theorems, and among the proof of them, also how to use them as well. So the first one is that angles in a... Let me do that again. Okay, so the first proof is that angles in a semicircle is 90 degrees. The angle in a semicircle is 90 degrees. So what we're saying here is that this angle is 90 degrees. Now, how to prove this? Well, we're going to prove this by using another proof, which we will now talk about. So this proof goes like this. If this is x, then this is always going to be 2x as long as it goes past the origin. So this is called angles at the center are double angles at the circumference. And this is shown here. So how do we prove this? How do we prove that angles at the center are double angles at the circumference? circumference. Well, let's attempt this. So let's say acknowledge this line here. And let's call this point A, let's call this point B, and let's call this point C. So this is line OA that I've just done here. So let's then call this, let's call this angle X, and let's call this angle Y. Okay? At this point, we don't know that this is 2x. So this angle is X, this angle is Y. Now we know that this triangle here, we know that this triangle here is a isosceles triangle because two of its sides make up the radius here. So knowing that this is an isosceles triangle then tells us that this side also equals x. This and this are the same. Now we can do the same with this side. We know that this angle here equals this angle because this is the same length as this, and therefore it's an isosceles, and the two bottom base angles must equal the same thing. So you've now got y. Therefore, since we know that there's 180 degrees in a triangle, this angle here is 360 minus 2x. And then this angle here is 360 minus 2y. And we don't know what this angle is here. But now we know that this angle is 360 minus these two added together. So 360 minus 2x plus 360 minus 2y. And over the 360s cancel out, and over here we get 2x plus y, 2x plus 2y, and 2x plus 2y is exactly this times 2, because this angle is x plus y, this angle is 2x plus y, and therefore that's proven that angles at the center are double angles at circumference. Now, I've never seen that one being asked to be proved before. However, I have seen this next one be asked to be proved before. So this next one is that angles at the circumference are equal if they stand on the same arc. So what it's saying here, so imagine this was the center. So it does go through the center. And it's saying here that angles at the circumference, so this one and this one is what we're talking about, are equal if they stand on the same arc. So they're saying that this angle is equal to this angle, and we're saying that this angle is equal to this angle because of the fact that they stand on the same arc. Now let's try and prove this. So what we're going to say is, we'll say, let's label them A, B, C, and D. And this is the center. So we know from the theory that we just said that angles at the center are double angles at the circumference, that if this is x, then this angle must be 2x, because I know it doesn't look like it, but this is a variation of that one. It's just a very, very tiny variation that looks like that. But nonetheless, it will still work. So we know that this is 2x. Now, we can easily prove that if this is 2x, this works the same way. So this must also be x. And that's a really quick proof. And we can do the same thing with the y's here. So let this be y, then this will be 2y, and this must also be y. And that's how you prove that one there. And that theorem is called angles at the circumference are equal if they stand on the same arc. Okay. So let's just get rid of that now. And do the next one. The next one is about cyclic quadrilaterals. So a cyclic quadrilateral is just a quadrilateral in which all of the sides are on the circumference, are found on the circumference. So this is an example of a cyclic quadrilateral. All four sides are on the circumference. So the theorem here is that opposite angles in a cyclic quadrilateral sum to 180. So we're saying that this, say that's A, and this B, we're saying that A plus B must equal 180. Now let's prove this. So the center is here. Let's say the origin is there. So what we're going to do is we're going to draw two lines. We're going to draw a line from here to there and a line from there to there. And let this be A, B, C, and D. Now what we're going to do is say, let this angle be x. Let BAC equals x. Now for BAC must equal 2x. Now let's do the same on this side. Let BDC equal y. That must mean that BOC must equal 2y. Now we have 2x and 2y. So we know that there's 360 degrees about a point. So 2y plus 2x must equal 360. So x plus y equals 180. Thus proving the theorem that opposite angles in a cyclic quadrilateral sum to 180. Okay. Let's now revise right angle theorem. So right angle theorem comes into account when we're saying that, say this is the center, and we say that a tangent to the circle at the point it touches the circle will form a right angle. Now we have to prove that this is true. So this is this is a hard one to prove. We do this by proof by contradiction. So we say that, let's call this point T, and let's call this point T2. And let's create a triangle here. So we can't assume that's a right angle triangle. So let's assume that OT is not perpendicular to this line, to T2 to T1. So we're saying that assume that this line isn't perpendicular to this line, because we're doing proof by contradiction, which basically means show that the opposite would not make sense. So then this is, because we can clearly see that this is a triangle. So this line is a hypotenuse. However, OT1 is actually bigger than OT, as it is the radius plus this bit here. So we know that okay, sorry, I was just getting my bearings. So what we're saying here is that this line here, so T2 to OT, is the radius plus this extra bit here. So this length of the radius plus, let's call this x. This is r plus x length. And O to T1 is x length. Now what we're saying here is that OT1 is if we assumed that this line isn't perpendicular, then let's assume that this line is perpendicular to this line. And that means that if that line was perpendicular to that line, then imagine that's at 90 degrees, then that's saying that this line is the hypotenuse. However, it doesn't make sense to be a hypotenuse because this is x and this is r plus x, but the hypotenuse is supposed to be the longest side. So that's how we prove a right angle theorem. It proves that if this wasn't perpendicular, then we're saying that if this line isn't perpendicular, then we're saying that this line is perpendicular. And if we wanted to say that line was perpendicular, then that means that we can create a right angle here, and then this side will be the hypotenuse. But this side can't be the hypotenuse because it's actually smaller than this side. I hope you understand it, and I hope I didn't overcomplicate it. But let's go to the next circle theorem. Okay. The next circle theorem is that tangents from a common point to a circle are always equal in length. So let's identify a point. Let's say this point here, and call it P point. So one tangent going like, oh gosh, I can't draw it. One going like this and one tangent going like this. So they both share the common point P. And we're saying that tangents that share a common point are always equal in length. So from here to here, we're saying that this length is always equal to this length. So how do we prove this? So we can prove this by drawing a line from this point here to here, and from this point here to here. And what we're saying is that, let's call this T1 and this T2. And we know that from the proof just earlier said of the right angle theorem, that a tangent is perpendicular to a radius. So therefore, this must be 90 degrees. The same thing here. This tangent, T2, is perpendicular to the radius here. So this is also 90 degrees. Now, if this is 90 degrees and this is 90 degrees, and then we can do a proof by proving congruency using triangles. So they both share. So imagine this line here. So what we're going to do is try and prove that this line is equal to this line by using congruency proofs. So we already know that this line here is exactly the same as this line here because they're both radiuses. So that's side. Then we've got the central line here, which they both share. So that's also side. And then they've both got right angles here. So that's right angle, or you can just call that angle. Or let's be smart about this. So this angle here, this side here that they both share, is actually the hypotenuse because we have right angles here and here. So therefore, proof by RHS, right angle, hypotenuse, and side, tells us that this side is equal to this side, and therefore tangents that come from a common point to a circle are always equal in length. You would prove that one. If you have any questions, feel free to tell me because I don't know how well I'm explaining this. We have two more circle theorems after this. Okay, let me just get rid of that. Okay, so let me just start over. So the next circle theorem is a line drawn from the center of a chord is perpendicular to the chord. So imagine this is the center. And this is a chord. So a chord is for example, looks like this. So we're saying that a line drawn from the center of a circle here, so like that, the diameter basically that runs through the circle, to the midpoint of a chord is perpendicular. So we're trying to prove produces a right angle here. So a way to prove this is by drawing out a triangle. And this triangle, because both of this side and this side are radiuses because they come from the center point here, we know that they are equal in length. So we can put these signs here. And if we know they're equal in length, we know that this angle is equal to this angle. And if we know that angle is equal to that angle, then we know that this is definitely an isosceles triangle. And if we were to just focus on this triangle here, let's say this is x, and that is also x, and that is side, and that is side. So far, we're going to use a congruency proof again. So they both share this side here, here, and here. They both share this angle here and here. And we know it's a midpoint of a chord, so this length is going to be exactly the same as this length. So that's another side and another side. So hence, by side angle side, they are proved to be congruent. And therefore, because they're proved to be congruent, that means that this must be a right angle, because this angle has to be the same. This angle has to be the same as that angle, but also half of 180 degrees. So that is how you prove that. And for the final circle theorem, excuse the epic drawings of a circle. The final circle theorem is that the tangent and the side of the triangle is equal to the opposite angle. So that's quite wordy. So imagine, let's draw this tangent here. Okay. Imagine that was touching there. So that's a tangent. And we've got a triangle here. Just a regular old triangle. And that is the center. So they're saying that the angle between the tangent and the side, so they're saying that this angle, let me use colors, they're saying that this angle is equal to that angle, and they're saying that this angle is equal to that angle. Prove that now. So we're going to use our trusty old circle theorem that angles at the center are double angles at the circumference. So let's label the angle A, B, C, and this is O. So we know that if we let BAC equals x, then we know that BOC is going to equal 2x, and therefore we know that because this side BO is equal to OC, because they're both radiuses, that this is an isosceles triangle. Therefore, this angle is over 2, which is the same as saying 90 minus x. And this is also 90 minus x. So now we know the sides of that. And now what we can say is that angle BC, angle BOC, so this angle here, is therefore 2x. So that means that BAC must equal x. So we're proving that Oh, so I've just done it the other way. Sorry if I'm confusing you. So we've got up to here. So we've got up to the fact that this angle is equal to this angle. So now what we can say is that this angle, we're trying to prove that it equals x. And therefore we have to prove that this, and we know that this is a 90 degrees because this is a tangent, and the radius also always makes a 90-degree angle. So therefore, CB is going to be 90 minus x, and therefore you just get x. So that's how that one is proved. Okay, so there are all the circle theorems done. We can now move on to the hardest part of GCSE maths, definitely, which is vectors. However, vectors require more practice, so I'm going to try and find some really good questions for you for the last sort of 20 minutes. Although there is a bit more trigonometry that we can do in terms of how to use the sine rule and things like that, but that's just more of third maths, I believe. So now we're going to do some vector practice. So I'm going to get you some vector questions and you can do them now. So you can now do this exam question. So this is a vectors question. And the first part is a 1 marker, but the next part of it is 4 marks. And these are the type of questions you're going to get. They are quite difficult, and that can just finish off our GCSE maths revision for today. If you have any more questions or would like me to go through anything in maths, feel free to just chat it in the live chat. And yeah. Okay, everyone, thank you so much for watching and joining the live stream. I'm now going to end the stream 10 minutes early so you can have an early 10-minute break. Again, thank you for watching and see you soon.